Welcome, I'm Mingzhe from Tsinghua University. In collaboration with Huawei, here we present our industrial practice of enterprise-level DBMS fuzzing with coverage guidance. GaussDB is the enterprise-level DBMS product of Huawei. To begin with, the QA team has been fuzzing GaussDB with GaussSmith, a customized version of SQLsmith. GaussSmith generates a large number of random SQL by its grammar rule, then executes them. Many bugs were detected with fuzzing. Recently, coverage-guided fuzzing has become a hot topic in the academia. By introducing coverage as feedback, the fuzzer can determine the quality of generated SQL. Thus, the ability to explore code is greatly enhanced. To bring coverage guidance to fuzzing practice, obtaining coverage is a prerequisite. Therefore, the first step is to compile the target system and fuzz driver with coverage collection enabled. However, compared to well-tested library-based DBMS, the introduction of enterprise-level features in industrial DBMS leads to extra logic. For example, GaussDB has around 466,000 basic blocks, only taking its core components into account. To support business on large scale, the core component is deployed on thousands of nodes. For state-of-the-art DBMS fuzzers, collecting coverage from a large number of basic blocks is imprecise, not to mention the span of binaries and nodes. Take Squirrel as an example. Although it expanded AFL's bitmap from 64 kilobytes to 256 kilobytes, the hash collision is still serious. For the best possible hash assignment scheme, 1.82 basic blocks still share the same counter. After building instrumented binaries, fuzzing can be started with the given initial corpus. In this step, we still found challenges in input generation. SQL is a complex standard with thousands of pages. For DBMS, most of them implement a sub or superset of the standard, creating a variety of SQL dialects. For testing tools, generating correct SQL is also a daunting task. For example, developers write tens of thousands of lines of code just to cover the most basic parts of PostgreSQL. As a result, the input generation is fragile because of the discrepancies between the SQL generation tool and the DBMS itself. As the fuzzer tests the target DBMS, unique corpora are preserved during the process, of which crash-triggering inputs are also saved. The developer must reproduce the bug with the saved inputs to analyze the root cause and fix the bug accordingly. However, in this step, we found a portion of the bugs are unproducible due to rich states of a DBMS. In other words, SQL only partially contributes to the concrete execution path. For example, external disk sort may be chosen if the working memory is insufficient. The average bytes of entries in a table may change the final execution plan, and whether a table is indexed determines the scan type. Sometimes, even executing the same query twice leads to vastly different execution traces. As the figure shows, obviously, inserting the same row again into an indexed table results in error. Therefore, some bugs are extremely difficult to fix because the developer can only obtain the original input, which cannot reproduce the bug. To overcome these challenges, we designed Rattle, a robustness-oriented fuzzer to perform coverage-guided fuzzing on enterprise-level DBMS. In a bird's view, it contains three components. First, when building fuzz targets, the precision of coverage collection can be improved with bijective block mapping for accuracy, and interbinary coverage linkage for completeness. Second, when generating SQL queries, the fragile SQL corpus-based mutation can be strengthened with dictionaries. Third, when investigating root causes, the analysis of unproducible bugs can be performed online with deduplication and rich context collection. The first solution is precise feedback collection. Our solution has two parts. First, at compile time, we instrument the program with one-to-one mapping from each basic block to its coverage counter. The generated binary eliminates coverage collision inside one binary. Second, at runtime, to ensure the precision where multiple DBMS components are running in parallel, we perform interbinary coverage linking. Here, the father computes the layout of coverage region for different binaries and processes. Our solution ensures that the hotness of each basic block inside each binary is precisely recorded. The second solution is robust input generation. To tolerate subtle differences of DBMS dialects, we enhance the SQL generator by relaxing the semantic checks with customized dictionary. The dictionary contains collected keywords used in a specific DBMS, and we apply dictionary-based mutation on the input generated by a grammar-based generator. Even if the generated SQL is rejected by the semantic validation, we still send it to the target DBMS. Although mutation-based methods will generate syntactically incorrect test cases, its robustness is still attractive in industrial environments. Finally, to handle unproducible bugs, we propose the third solution of online bug triage. The anomaly analyzer traces all threads by listening to signals, and it also keeps a ring buffer to store the last output of the standard outputs. More than just saving the crash triggering input, the analyzer can also collect rich context, including the coverage feedback, stack trace, and termination log. The context is saved along with the original input. In most cases, the developer only needs to read the saved context to fix the bug. After applying these solutions to our industrial practice, we performed coverage-guided fuzzing on several enterprise-level DBMS. More than fuzzing GaussDB alone, for proper evaluation, we extended our targets with Bloomberg's distributed DBMS COMDB2 and the original PostgreSQL, where GaussDB derived. From the results, we find that while black box fuzzing is relatively simple in design, it still has good robustness in industrial practice. For example, the black box fuzzer SQLsmith outperformed the coverage-guided fuzzer Squirrel by 151%. However, despite the robustness, black box fuzzing is still limited by grammar models. For example, the advanced oracles of SQLancer performed well on PostgreSQL, but when adapting it to GaussDB, a PostgreSQL-based DBMS, trivial differences in syntax prevented it from function normally. Finally, by following the robustness-oriented approach, Rato successfully applied coverage-guided fuzzing to enterprise-level DBMS. Compared to industrial black box fuzzer SQLsmith and SQLancer, as well as coverage-guided academic fuzzer Squirrel, Rato covered 38, 106, 5 and 83% more basic blocks than the best results of other three fuzzers in GaussDB, PostgreSQL, and COMDB2 respectively. We used Rato to test GaussDB continuously and discovered 32 previously unknown bugs in GaussDB. It also discovered dozens of bugs in other DBMS. That's all. Thank you. Any questions?
Hi again, everyone. Welcome to the last Q&A session of the testing automation session. Today, we have the paper titled Industry Practice of Coverage-Guided Enterprise-Level Database Management Systems, Fuzzing. This is a paper in the Software Engineering in Practice track, and we have the pleasure to have Mingzhe Wang here with us to answer any questions you might have about this work. Mingzhe, thank you very much for being here. Let's wait to get some questions from the chat. And in the meantime, perhaps I could ask something myself. So you mentioned that you discovered several unknown bugs in the different DBMS that you looked into. So the numbers vary a little bit, right? So I can see that for PostgreSQL, you found very, very few bugs. Could you make some sense of all these bugs that you found? It's like nearly 100 altogether. Is there some commonalities in the type of bugs that you can find with your fuzzing tool?
At the moment, our tool is mainly focused on memory-related bugs and some undefined behaviors such as signed integer overflows. So our coverage-based approach can be adaptive and applied to many types of bug detections, such as racing conditions. But at the moment, we're just focused on the types of bugs of memory-related ones. So, in summary, the coverage-based method can be adaptive, and at the moment we just use the robustness-oriented approach to fuzz memory bugs. But I think in the future we can adapt it to other types of bugs. That's all.
What would this adaptation entail? What kind of changes could you have to make to your approach to be able to target other types of bugs?
Yeah, that's kind of complete. For example, to adapt to PostgreSQL, we just need to modify the client program of PostgreSQL, i.e. PSQL, so that we can just ensure our tools generated input are sent directly to the client. Then the client sends the command to the server. In this way, we can easily adapt our tool to many kinds of DBMS. So, please.
No, go ahead.
This approach can be robust because generating inputs and obtaining the queries from the standard input is a common practice in the industry. No matter what kind of DBMS you use, for example, Postgres, MySQL, or even the embedded one, SQLite, all of them accept inputs from the standard input. So our tool focus on this part. So it is very easy to adapt to other DBMS.
At some point in your presentation, I think you said that the input test generation for SQL queries can be very fragile or very just not very good. Have you considered using one of these very clever approaches, like for example, this input from hell work, where they try to generate more, let's say, critical queries? Have you looked into that using grammar-based test generation, let's say?
Because our method is based on grammar, so we think it is the best if we can strengthen the robustness of existing approaches instead of adapting to more methods. But yeah, that's a good idea. So I think maybe in the future we can try some more ideas to think beyond the box of grammar-based generation. Thank you.
I'm still asking my questions because I don't see people asking many questions. So it's almost like a coffee break now.
Great.
So you also mentioned that you improved the robustness by using a dictionary. Could you please elaborate on, first of all, how you implement this dictionary into the approach, and second of all, did you evaluate the effect that implementing this dictionary customization has on your approach?
Yeah, that's a very good point, because the robustness, because our paper is focused on robustness, and robustness is usually overlooked in other works. So the robustness of our grammar-based generation mainly come from two parts. First, the dictionary-based one, we can use the dictionaries, the tokens generated from the source code of the DBMS programs. For example, there are many customized or extensions to the NC-SQL in PostgreSQL, and they all begins with PG underscore. So if we harvest the tokens from the PostgreSQL's codebase and extract these tokens, then we can build a comprehensive dictionary of the domain-specific extensions of PostgreSQL. So this is the first part. We can extract and build a dictionary from the source code. And for the other part, i.e. the relaxed semantic checks, the intuition is simple, because if we just generate semantically correct inputs, then the error handling code of the grammar-based part can be difficult to trigger. It is very difficult to trigger. For example, you just enter SE column, such obviously wrong input based on the grammar-based approach. But indeed, we just discovered that it is very common to trigger more logic if we can just generate some semantically and grammarly incorrect inputs. So we just relaxed the semantic check and the grammar check of the based approach, i.e. the one I think is based on polyglot. So with the relaxed checks, we can explore more scenarios and to make the generated inputs more robust and explore more scenarios.
Did you run any experiments to see how your approach performed with and without the use of the dictionary?
That's a good point, because indeed we did some preliminary experiment, and the result is the result is significant. So we just extended our work with the robust dictionary-based generation. But due to the page limitations, we cannot present all the results in the paper. So only the main contributions are separately evaluated instead of the corner case, such as the effect of the effect of dictionary-based robust input generation.
Sounds great. Yes, I understand. Well, thank you very much, Mingzhe. I don't think there are more questions from the audience, so I appreciate your answers, and thank you very much for the nice paper and the nice presentation.
Thank you for the questions too.
Thanks. So for the audience, thanks for attending this session. This was the last paper of the session, titled Testing Automation. And I hope you enjoyed the last day of the conference, and I hope to see some of you in the workshops during the weekend. Thanks, Mingzhe. Bye-bye.
Thank you. Bye-bye.